All right, we are going to look at inclined planes today. Inclined planes without friction, to be specific, and how Newton's laws apply to them. Now I'm going to show you a couple tricks we use when we solve inclined plane problems. So the first trick is we identify the direction of the acceleration. And so in this case, it's pretty safe to say that a block on a frictionless incline is going to accelerate down the incline. Now notice when I drew the acceleration, did I draw it on the object? No, because accelerations aren't part of our free body diagram, so keep that in mind. So I've identified the direction of the acceleration. The next step, once you've identified the direction of the acceleration, you're going to want to identify your coordinate system such that the acceleration is only in one dimension. So in other words, I've rotated my coordinate system, so now my x direction is the same as the direction of the acceleration. Now, this turns out okay for most part. So when I draw my normal force, here is my normal force. Normal, remember, is perpendicular to the surface, so the normal force is in the y direction. But when I draw good old gravity, mg, it's not only in the x direction or only in the y direction. It's kind of at an angle. So I'm going to have to resolve it into components. So this is the second thing I wanted to show you about inclined planes, is how we draw that mg vector and then how we resolve it. So gravity always acts straight down toward the center of the earth here. And so maybe I'll draw that a little further. So this is the direction of that force of gravity, mg. Now you'll notice that it acts straight down, so this is a 90-degree angle. Okay. And now we do want to resolve it into components. Okay. And you'll remember that my coordinate system has been rotated here. So I need a component that's perpendicular to this surface and a component that's parallel to this surface. And when I draw those components, I'm going to draw them like this. Okay. So this is my 90-degree angle. Oh, you should practice this. Watch that section of video again, pause it, do something, practice this. Make sure you can draw resolving it into those components. All right, now that you can draw it, what we're going to do is we're going to figure out the angle. So typically we're given the angle of the incline. We'll call it theta here. Okay. Now let's just throw some numbers in to make our life a little easier here. So I'm going to say theta is 30 degrees. Okay. And from what I know about triangles, what's this angle going to be? Well, they all got to add up to 180, so this has to be a 60-degree angle. So it's our good old 30, 60, 90 triangle. Right. And you'll note that I said this component must be perpendicular to the surface because my y-axis is. So what that means is these two angles have to add up to 90. So if this one is 60, this one is my angle theta. Okay, so when we draw this, there is going to be a link between the angle of the incline and the angle between mg and your perpendicular to the plane component. All right, so let's go ahead and finish our free body diagram and solve for our acceleration and our normal force. We're going to practice that normal force one because we'll need it when we do friction. All right. Here we go. So I have to resolve mg into components. So there's going to be a component perpendicular to the surface and a component parallel. This angle here is going to be theta, so the one adjacent is going to be mg cosine of theta, and the one opposite the angle is going to be mg sine of theta. Now again, it's nice to redraw that free body diagram only using the blue arrows, and I'm going to actually rotate it back a little bit here. So now I have mg cosine of theta pointing into the table or into the plane. Mg sine theta is down, and the normal force is up. Now the reason I rotated it a bit here is this looks very similar to what we were doing before. Okay? So, speaking of similar before, we are going to be looking at Newton's second law, ma, and again these are vectors, so we're going to break them into components again. So we're going to sum up the forces in the x direction, and we're going to sum up the forces in the y direction. In the x direction, that's the direction I determined my acceleration to be in. Ideally, we want our acceleration in just one dimension so that that component of the acceleration is the acceleration, and then it will not be accelerating in the y direction because it's not accelerating off of the incline or into the incline. So here we go. We're going to add up the forces in the x direction. So I have mg sine theta. Now you'll notice that's a positive value. That's because I pointed it down the incline. I like my acceleration, my x direction to be in the same direction, so I always get positive acceleration. What's kind of cool here is the m's cancel out. This means I can put any block on there and it will accelerate down the ramp at the same time. Now this is assuming we have no air resistance, no friction, all of those wonderful conditions. So my acceleration is going to be 9.8, because remember g is just a positive 9.8, times the sine of 30. And so my acceleration is 4.9 meters per second squared. Now what about the normal force? Well, the normal force we usually solve for in the y direction, and there's no difference here. So in the y direction, I have normal force minus mg sine of, mg cosine of 30 equals 0. So the normal force is now mg times the cosine of 30. And so you can type that in your calculator. You'll get a normal force of 127 newtons. We'll need that when we do friction.